Peter Johnson is a co-founder and research team lead developing quantum algorithms at ZAPATA Computing. He received his PhD in quantum information at Dartmouth College with Lawrence Aviola. And after graduating, he moved to Harvard University to research in near-term quantum algorithms as a postdoc in the group of Alana Spuruguzik. And he continued this work in near-term quantum computation in his team at ZAPATA Computing, trying to achieve quantum advantage. And he will present the minimizing estimation runtime on noisy quantum computers, which is also, it's the squeezing the lemon thing, right? Go ahead, whenever you're ready.
Okay. So are people able to see this?
Yes.
And you can hear me okay? Yeah, well, first of all, thanks, Tim. That was a great talk, super interesting. And maybe there will be some ways that these could even interact. And yeah, thanks, Mihao and Alba, for the invitation to give this talk. So I'm going to be talking about some recent work that we did on the ZAPATA research team with Guoming, Dax, and Yudong and myself. You can find 2 papers about this work on the archive from back in June. And we've been excited to see that over the past few months, quite a few other papers have come out on related topics. So this seems to be a pretty exciting area to be thinking about. So before diving into any technical details, I want to invite you all to a particular headspace. And this is the headspace that we were in when carrying out this work. So I imagine for many of you, and it's definitely the case for us, that we spend quite a bit of time thinking about what can we do with today's quantum computers? Like, what's that, the like N+1 that we want to improve about them? In this work, we were actually in more of the headspace of thinking about when quantum advantage will be achieved, what do we need of those future quantum computers? And so to set this context a little more, I want to send out a poll. So feel free to throw your answers in the chat. But one thing that I want you to keep in mind throughout this talk, and we'll get to this at the end, is imagine that you're given a choice in the design of or capabilities of this quantum advantage machine. You can choose the red pill. So that is a machine which has gate error rates on the order of 10 to the -6 and gate speeds of 100 microseconds. So this quantum advantage machine is a little noisy, but it has very fast gates. The blue pill, on the other hand, has much better error rates of 10 to the -8, but the gate speeds are a bit slower. So a question to keep in the back of your mind during this talk is, if you were, say, trying to design some quantum error correction scheme, or you were trying to design quantum gates, or you are an investor having to choose, okay, which company am I investing in? This red pill versus blue pill is a likely question to come up. So the purpose of this talk is to consider a particular task of a quantum computer that will come from quantum chemistry. And by considering what the state-of-the-art method, VQE, is able to do, we'll be motivated to consider an improvement on VQE, and it will put us in a position to answer this question of which device, the red device or the blue device, will be better for solving quantum chemistry problems. Okay. So to start, we'll get to our beloved quantum or variational quantum eigensolver algorithm. So why do we care about the variational quantum eigensolver? Well, this allows us to predict molecular properties such as binding strengths, reaction rates, molecular pathways. And what it does technically is give an estimate of the ground state energy of a Hamiltonian describing a molecule. Recently, there have been quite a few experimental demonstrations of VQE. And in parallel, there have been a ton of algorithmic advances. You might recognize a few of these, right? Coming up with different designs of ansatses. This is something that Tim brought up. Considering different classical optimizers to use. The point that I want to make here, though, and maybe if there's nothing else that you get from this talk, it should be this, is that to date, there is no evidence in the literature that the VQE algorithm will be able to outperform state-of-the-art classical methods. And this is the starting point for this work. In thinking about the quantum advantage machine, it's possible that VQE won't cut it. So why might VQE not cut it? So in order to appreciate this, we'll dive a bit more into the algorithm itself. Oh yeah, and maybe the question is like, okay, will the quantum advantage machine use this standard VQE algorithm? Okay, so VQE uses the variational principle for estimating the ground state energy. The way it does this is that you prepare an ansatz state on the quantum computer, and then you tune the parameters of this ansatz to try to yield the minimum energy among the parameters. This minimum energy is taken to be an upper bound and an approximation to the ground state energy. So the way this is carried out is in an iterative fashion. So with each quantum state preparation, we carry out an estimation of a number of expectation values. These are then fed into a classical processor, which decides how to update the ansatz parameters. This process is carried out in a loop until a convergence in the energy estimate is achieved. So why VQE? Why might VQE not cut it? So it turns out that there's one small step in VQE, which is actually quite expensive. This is the task of estimating expectation values. So how does VQE estimate expectation values? So VQE uses a method that we call standard sampling. So for the goal of estimating the expectation value of, say, this polystring with respect to the ansatz, standard sampling prepares the ansatz and then measures in that poly basis, receiving a one of the two eigenstate outcomes. Much like estimating the likelihood of heads of a coin, we collect many samples and then use the sample mean as the estimate. So unfortunately, this process is very slow at giving information about that likelihood of heads. So to give a sense for this, I have a video here. And so this video shows how with each coin flip or measurement, our beliefs about the various true probabilities of heads converges towards the true probability of heads. And as you can see in the simulation, this path of the precision in this estimate follows this well-known statistical 1 over square root of n profile. So it is this 1 over square root of n, which is notoriously slow and creates a bottleneck for the VQE algorithm. Okay. So this leads us to this lesser known measurement problem of VQE. And it's coming from the fact that the standard sampling leads to a 1 over square root of time reduction in the estimate of error. And it's important to point out that this is a bottleneck not only for noisy quantum computers, but also for error-free quantum computers. If you ran VQE on a perfect quantum computer, the scaling of this precision over time will also have this slow profile. So is there any hope for improving upon this? Well, yes. It's long known that using quantum phase estimation, you can improve this scaling to a 1 over t decrease. Of course, the downside with quantum phase estimation is that it requires very deep quantum circuits. And so with noisy quantum computers, we're limited in the depth of circuits we can implement. So is there any way to strike a balance between these two extremes? So yes, just last year, this really exciting work was put out by some folks at Riverlane called alpha VQE. And alpha VQE gives a theoretical framework for tuning this scaling, hence the alpha. So as an example, you can achieve a 1 over t to the 3/4 scaling. And the circuit depth controls the scaling. So we were very inspired by this work. And so we wanted to take a more bottom approach to improving the performance of estimation. So that approach is, given a noisy quantum device, how should we optimize the rate of information gain in amplitude estimation? That is the estimation used in VQE. So the principles that we used here were to incorporate the effect of errors directly into the design of the algorithm, and to try to maximize the rate of information gain with the resources available. And lastly, we also tried to so-called trim the fat in the quantum circuit. So removing ancilla qubits when they're not needed, and to cut down on circuit depths. So for the last half of the talk, and I want to make sure I'm doing okay on time. Yeah. I'll introduce this technique that we call enhanced sampling for improving the rate of information gain with noisy quantum computers. So let me give a gentle introduction into enhanced sampling. So beginning with the standard sampling circuit, where you can imagine the goal is to estimate expectation value of this polystring. Enhanced sampling circuits are just a slight variant of the VQE, or standard sampling circuit. So we apply the polystring as a gate, then we invert the ansatz, apply the Grover-like reflection about the initial state, and then reapply the ansatz. So this chunk here we refer to as a Grover iterate. And then we measure the polystring of interest, getting again a 0 or a 1. And we note that the circuit, unlike phase estimation, does not require any ancilla qubits. The question, though, is, as we're receiving this data, how should we process it to yield an estimate of the expectation value? So the answer to this question is that we must consider what the likelihood function is generated by these enhanced sampling circuits. So in VQE, the likelihood of 0 versus 1 was linearly related to the expectation value of interest. It turns out that with this enhanced sampling circuit, the likelihood function is a cubic with respect to the parameter of interest. In particular, it takes the form of a Chebyshev polynomial. And the reason why this has the chance of improving information gain is that this new likelihood function is more sensitive to the parameter of interest. Small changes in the parameter of interest produce large changes in the observed data. So we call this likelihood function a Chebyshev likelihood function. Now, compared to standard sampling, we can play the same movie, comparing how the information gain in the two cases changes. So as we see that with each measurement, the estimate coming from enhanced sampling is narrowing around the true value at a much faster rate than that of standard sampling. And keep in mind that this is just like a slight variation of the VQE circuit. So we can quantify this measure of information gain using what is called the Fisher information. And it turns out in the case where there is no noise, the Fisher information is a factor of 9 larger for this L equals 1 enhanced sampling circuit. Now, in practice, the circuit will accrue some error. So we need to incorporate this into our expectations for estimation gain. So we can imagine that the effect of error is to alter the likelihood function from which the samples are being drawn. It turns out that with a slight attenuation in this likelihood function, it actually can cause a pretty dramatic change to the Fisher information. And in particular, we can be like affected by these so-called dead spots. If I had more time, and maybe after the talk we can get into it, I would love to talk about how we get around this effect of these dead spots. And actually in the two papers, I would say like 95% of the work was spent trying to improve this dead spot phenomenon. For the rest of the talk though, I will not focus on the effect of these dead spots, but rather consider the cases where there's not as bad of a reduction. So in general, how do we consider the effect of error in enhanced sampling? So there's a balance to strike. We expect that as we use deeper and deeper enhanced sampling circuits, we stand to improve the sensitivity of the likelihood function on the parameter of interest. But at the same time, there's a decrease in the overall circuit fidelity. So we expect there to be a balance to strike in trying to optimize the rate of information gain per time. And so that is incorporating these two factors. A quick back of the envelope calculation shows that we expect the optimal number of layers to be proportional to 1 over this decay factor. So as for a quantum computer where the noise is not accruing as much, we can afford to use deeper enhanced sampling circuits and accordingly increase the rate of information gain. So we developed a model which is effectively like integrating this Fisher information per time. There's a bit more to this calculation, but we arrive at a model for the time needed to achieve a particular accuracy in estimation as a function, in this case, of 2-qubit gate fidelity. And what we see is an interpolation between the VQE type scaling, known as the shot noise limit scaling, and the Heisenberg limit scaling, which is indicative of phase estimation. So this is the model that we will use to answer the question from the beginning. How do we choose between a noisy, fast quantum computer and a less noisy, slow quantum computer? And we can imagine that the quantum advantage machine will need to carry out fast estimation. So this warrants using this model as a guide for choosing the red versus the blue pill. So for the last few slides, I'll show some plots with this model. So we'll consider a case, maybe the quantum advantage machine will want to use 100 logical qubits. Maybe for VQE, we'll want a 2-qubit gate depth of like 200 for estimating expectation value of a Pauli operator. And right, we want to consider these two different 2-qubit gate speeds, 100 microseconds versus 100 milliseconds. And we'll imagine that the target accuracy we desire is 10 to the minus fifth. So we will plot this runtime to target accuracy as a function of different gate fidelities for these two different quantum computers. Here's what we find. So I'll just start with the blue quantum computer. So as the 2-qubit gate fidelity improves, we can afford to use deeper enhanced sampling circuits and therefore reduce the runtime. But at a certain point, we hit this Heisenberg level scaling. And so there's no, for all intents and purposes, you would be working with a perfect quantum computer. So that is this transition to the flat region. Same thing goes for the red quantum computer. Now, to answer the question of red pill versus blue pill, for the fast quantum computer, we consider the case of 10 to the minus 6 being the error rate. And the runtime achieved is about a month. For the slow quantum computer, it has better gate fidelity, so we can afford better enhanced sampling circuits. But due to this slow gate speed, it will actually take that quantum computer a year of running in order to achieve that accuracy in the estimate. So this shows that it is better to choose the red pill, according to this model, because you will be able to carry out estimation a factor of 10 faster. Okay, so just to conclude, these enhanced sampling circuits, or what we also, a variant of them called engineered likelihood functions, are a promising antidote to the measurement problem. It shows how increasing the fidelity leads to a time savings in estimation, an essential task for many quantum algorithms. Demonstration of this technique are possible on today's devices. And we expect this technique to be useful before and into the fault-tolerant regime, where small amounts of error will still occur. So looking to the future, areas of impact for improving estimation are in a wide variety of applications. Also considering estimation as an important subroutine, this can have an impact on how we should design hardware. You know, how do we balance the trade-off between error rate and gate speed? And finally, this is not something that I've talked about yet, but this points to the importance of noise characterization. We must sufficiently characterize the effect of noise on the likelihood function in order to properly carry out estimation. Okay, so with that, thank you. And I would love to have a discussion and hear some questions.
Thank you, Peter. I just mind blowing the one of the last slides with the red versus blue. Very interesting. I never thought about the measurement problem with PQE, so thank you. Okay, any questions? It seems like Philip has a question. Could you just ask the question directly, Philip?
Yeah, I can do that. Thank you. Hi, Peter. It's Philip.
Hi, Philip.
Yeah, so I didn't really get the grower part of your algorithm. Like, what are you searching for? I didn't really get that.
Okay, great question. Oh yeah, sorry. I also should have said, like, you know, ZAPATA is hiring. I encourage people to apply for internships and postdocs. Please reach out to me if you have questions. Okay, Philip, great question, right? I brought up the concept that here we go, that this part of the circuit acts like a Grover iterate, right? So we are not carrying out quantum search, but instead we are carrying out quantum amplification. So we're using a Grover iterate to alter the way that the expectation value influences the likelihood of receiving a 0 outcome. And as you can see here, the function which describes this is this like cosine of, okay, a number times some angle. So this angle here is completely analogous to the Grover rotation angle. And as we change L, as we use more layers, we can increase this number, meaning that you do more Grover rotations.
Okay.
So this influences the shape of the likelihood function, and effectively it makes it more squiggly. And the more squiggly it is, the more sensitive the sample data is to the parameter of interest. You can imagine that if you just change pi, this expectation value, a little bit for a very squiggly likelihood function, you would expect to observe, for example, way more zeros. So I would say the general umbrella is this concept of quantum amplification. Quantum amplification can be used to boost the likelihood of a particular outcome, so that's Grover. Quantum amplification can also be used to enhance the sensitivity of the data to a parameter of interest.
Okay. Yeah, okay. Thank you, Peter.
And I have to admit that it really wasn't until working on this project that I had some understanding of the relationship between Grover search and phase estimation or amplitude estimation. So they're like, you know, two applications of one technique, the technique being quantum amplification. Yeah, and
Any other questions?
I would have one.
Hey, Tim.
Yeah, Peter, great talk. Thank you. So it's about the red and the blue pill. So how rigorous are they meant to be? So one of them has a 2 orders of magnitude longer gate time, but then a 3 orders of magnitude different error rate. or no, the other way around. So how did you choose that trade-off? And is that like, how did you motivate that trade-off?
Oh, actually, let me go here.
And I guess that plays on into your final slide then as well, on like
Yeah,
how the different, like these different trade-off charts, these like Pareto, whatever charts happen, right?
Right. So, okay, if I understand your question, it is like, you know, how do I choose these arbitrary seeming numbers? Okay. So for sure, I like reverse engineered this, and you know, I wanted to be a little bit like you know, Morpheus-like, where there's something appealing about the blue pill. You know, it's a safe place to be. You have a very you know, like very low error rates. You're like, oh, I could go to town with this quantum computer. Whereas the red pill seems like kind of dangerous and risky, like you're you know, having to grapple with the effect of like, you know, dirty error. So I intentionally chose these two values so that I could trick people into choosing the blue pill.
Mm-hmm.
But the like, at least in this linear or shot noise limit regime, the runtime of estimation is related to the product of these two quantities. And so, you know, I deliberately chose two sets of values so that the product in one case would be 10 times faster.
Okay, and if the product was the same, you would get a much more favorable trade-off between them, right?
Right. So this would predict, and right, this is definitely an oversimplification. There are like a rabbit hole of like details behind this, but just like the coarse-grained picture remains.
Okay. So thank you very much once again, both Tim and Peter. It was really, really interesting two talks. I will stop the recording now, and we'll have, you know, we can discuss it more afterwards. And thank you everyone who attended today. I hope it was as interesting for you as it was for me. And I hope to see you again in the next QRST in a month from now. Bye.